Right, so I want to do an example of the Cram-chelate. This is a slight an important variation on the Felkin-Anh model that we've already looked at. In fact, sometimes it's known as the Felkin-Anh chelate, although technically Cram was the person who originally proposed this. There's some slight modifications, which is why the name changed, but that's not important. The important thing here is that when you have a metal that can chelate, such as magnesium, so Grignard reagents are very typical for this type of reaction, or this type of model. Magnesium or zinc are absolutely excellent in this. It locks the transition state into a particular conformation, which then controls the real psi-phase addition of the nucleophile. So we need to answer a question like this, we need to start doing exactly what we've done before, and that is we want to look at the Newman projection. So we're going to stick our eye looking down this bond over there, and so what we see is this, and directly below us is the phenyl over there on the side. That's hydrogen, and this is the OMe over there. All right, so that's our initial Newman projection. Now, during the reaction, some magnesium is going to coordinate between the oxygen of the carbonyl and one of the other oxygens. There has to be some heteroatom for this to occur, by the way. So in this case, it's oxygen. That is going to bring those two close to each other. And so when the chelation occurs, so you write there chelation, we're going to redraw that and then look at the conformation that we have, and then make a decision as to which phase is going to happen. So we can put the magnesium chelating. So I'm just going to put that into inverted commas, and it looks, so that's twisted around over there. So the phenyl group is over there, and the H is on that side over there. And now, considering the Berge-Donitz trajectory, we can see that this side over there, which is the top face, because it's that side over there, all right, which is the top face of that side is prevented from attack because of the phenyl ring, whereas this side over there is actually accessible for nucleophilic attack, which means that the ethyl group actually comes in from the bottom face. So we would write that it prefers attack here, and we need to tell everyone why it prefers it over there, because there's least steric hindrance in Berge-Donitz trajectory. Right. So that would be the kind of like explanation for what's happening over there. So it's adding to the bottom face. And so when we draw out the product over there, what we need to do, so there's a number of different ways, as we've looked at, keep everything the same over there. Now, as the nucleophile comes in from the bottom face, it's going to push the OH up, but we mustn't forget that there's a hydrogen there. And that hydrogen is going to still stay in the plane. So the nucleophile came in from the bottom, which is the ethyl group, so it's like that, and the OH the oxygen ended up going up, which on protonation would end up looking like that over there. Now, as far as a product is concerned, this is absolutely fine to do it that way. If we want to get the zigzags, we need to turn things around and get them into that place, and in doing so, we're actually going to change things slightly. So we just need to make sure that we do it correctly, and so we would want something to look like this. And now this ethyl group is pointing at the back. We're going to move it slightly forward to get into line over there, which means that the hydrogen is actually going to go down and the OH is actually going to be pointing up over there, like that. And so that's another way of drawing out. But however, it's actually completely fine just to leave the product like this. Just some other important points of theory over here. You might say, well, why this works really well because of the chelation. So it holds everything in together, which is excellent. But something else that it does is that when the magnesium coordinates to it, it's acting as a type of a Lewis acid, and it's activating this carbonyl. So the reaction's a lot faster when that happens. The magnesium that's coordinating here is not just from one molecule of ethyl magnesium bromide, or at least the one that's going to deliver the ethyl. Be careful about that. The nucleophile is this whole thing over here. So when the nucleophile comes in here, it's ethyl magnesium bromide. This magnesium will be from another molecule of this, or some other magnesium that is now floating around in the solution after the initial reaction. So just think about that from a stoichiometric point of view. All right, there we go.